Okay, ready for another example. So let's take a look at this one right here. So here's our polynomial. P of x is 16x to the fourth minus 32x cubed plus 12x squared plus 4x minus 2. Okay, so let's first start by taking a look at the degree of the polynomial. It's a degree 4 polynomial. The highest power of x is 4. So we're expecting 4 roots at the very end. So at the end of the day, we should have 4 roots to this polynomial. Okay, so let's find them. So let's start by using our rational root theorem. And let's create a list of possible rational roots to start trying out. So remember, we start by making a list of the factors of the constant term, the term on the end that doesn't have an x. So in that case, that's 2. Now again, remember, if it's a negative, we just ignore the sign. We just look at the number. So factors of 2, those are easy. That's just 1 and 2, and that's it. So next, we make a list of the factors of the leading coefficient. Leading coefficient is the coefficient of the highest degree term, okay, which in this case is 16. Highest degree term is 16x to the fourth, so the leading coefficient is 16. And again, we would ignore any signs that go along with it. So factors of 16, 1 and the number itself, those are always factors, so 1 and 16. In addition, we have 2 and 8. And then 4 and 4, we don't want to repeat it twice, so just 4. Okay, so these are our factors of the leading coefficient. So the rational root theorem, remember, tells us that in order to make a list of our possible rational roots, we take all the combinations of the numbers from our first list over the numbers from our second list. So these numbers over divided by these numbers, and plus or minus, could be positive or negative. Okay, we would eliminate, we would simplify and reduce any fractions and eliminate any duplicates. Okay, so when that is done, what we get is actually not too bad. You might think it's going to be a real long list, but it's actually not too bad. So here's our list of possible rational roots. So it's plus or minus 1, plus or minus a half, plus or minus 16, plus or minus 1/8, plus or minus 1/4, and plus or minus 2. Okay, and that's it. Any other ones were duplicates. So once we reduce and simplify and eliminate duplicates, this is what's left. So these are the unique roots. Okay, so not too bad. Not too bad. So let me make some space here so we can start to do the work. So now comes the trial and error process. So we've got to start trying numbers from our possible roots list until we find enough of them that work that we reduce it down to a quadratic. Because once we get down to a quadratic, then we can either hit it with factoring if possible, or at worst, we may have to do the quadratic formula. Okay, now let's think about it. So it starts as a degree 4 polynomial. So degree 4. Every time we find a root that works from our possible root list, that's going to reduce the polynomial down 1 degree. So when we find the first root, it's going to take us down to a cubic. X cubed will be the highest power. Still not there yet because we got to get down to a quadratic, x squared, in order to be able to either factor it or use the quadratic formula. So we've got to find another one, and then that will get us down to a quadratic, a square, and then we can solve it. Okay, so we're going to have to find 2 roots from our possible root list that work before we can finally get it down to the point where we can solve it directly. Okay, so it's going to involve a couple of rounds of guess and check. Okay, so let's do it. So let's do our synthetic division. So we set it up, put our coefficients 16, negative 32, 12, 4, and negative 2. Okay, we put our little separator lines, and let's just start. So let's try 1, easiest one. So we drop the 16, drop the first coefficient, multiply. 1 times 16 is 16. Add it. Negative 32 plus 16 is negative 16. Multiply. 1 times negative 16 is negative 16. 12 plus negative 16 is negative 4. Multiply. 1 times negative 4 is negative 4. 4 plus negative 4 is 0. Multiply. 1 times 0 is 0. Negative 2 plus 0 is negative 2. Okay, remember what we're looking for. So the last term on the right, that's our remainder. And we're looking for remainder 0. Remainder 0 means that we found a root, that the factor that we divided in goes in evenly, and so that must correspond to a root. Okay, not there yet, -2. Okay, so we got to try another one. So let's try the next one. Okay, so well, why don't we try -1 then? Okay, so let's set it up again. So we got 16, -32, 12, 4, and -2. Separator line. So let's try -1 as our next shot. So drop the 16, multiply. -1 times 16 is -16. Add it. -48. Multiply. -1 times -48 is +48. Add. 12 plus 48 is 60. Multiply. -1 times 60 is -60. Add it. 4 plus -60 is -56. Multiply. -1 times -56 is +56. And you can already see we're not there yet. So our remainder is 54. Okay, that's not what we want. So we got to keep going. And hopefully, eventually, we'll be lucky and we'll be able to find one. Okay, so what's next on our list? Well, it looks like 1/2. Okay, so let's try that next. So let's set it up. 16, -32, 12, 4, and -2. Separator line. Okay, let's try a half. So drop the 16. Multiply. 1/2 times 16 is 8. Add it. -32 plus 8 is -24. Multiply. 1/2 times -24 is -12. Add it. 12 plus -12 is 0. Multiply. 1/2 times 0 is 0. Add it. 4 plus 0 is 4. Multiply. 1/2 times 4 is 2, and this is looking up. -2 plus 2 is 0. So we got it. Remainder 0. Okay, so we found one of the roots. X equals 1/2. Okay, there we go. X equals 1/2 is a root. Okay, but remember, we're not quite there yet because we're only down to a cubic. If you look at the coefficients of the quotient polynomial left, leaving off the remainder, the 4 would be a constant term, the 0 would be the x to the first term, -24 would be x squared, and 16 would be x cubed. Okay, so we're not quite there yet. We're still x cubed. Better than what we started with. We started with x to the 4th. But we're still not to the point where we can solve it directly. We don't have the quadratic formula to use yet, or factoring. Okay, so we're going to have to continue and find one more root that works. Now, when we do that, do not go back and start with the original set of coefficients. Okay, so in other words, don't go back and start with these guys right here, 16, -32, 12, 4, -2. What you're going to do is you're going to bootstrap it from these right here. So this level right here, this quotient polynomial that we found once we found the first root, 16, -24, 0, and 4. Okay, leave off the remainder, but take these coefficients. So when we do synthetic division for the next round, we're going to use these, okay, not these. If you went back and used these, you'd kind of be going in a circle because you wouldn't really be reducing it down, because once you find your next root, you'd still be at a cubic. Okay, so you gotta start with these guys right here, 16, -24, 0, and 4. Okay, so let's do our next round. Okay, now when you do the next round, you are allowed to go back and use the ones you already tried over again. Okay, so you can start at 1 and -1, 1/2, -1/2, and so on. Okay, so it might turn out that some of the ones that you used before may actually work again. Okay, so don't be afraid to go back and try those out. Okay, so let's try another one. And we're going to use, this time we're going to use these coefficients as our starting point. Okay, now I want to demonstrate something with this one. So I said that you can use roots over again. So let's say we tried 1/2 again. Let's say I have a hunch that that one might work again. And I want to explain something about that. So let's try it. Drop the 16, multiply. 1/2 times 16 is 8. -24 plus 8 is -16. Multiply. 1/2 times -16 is -8. Add it. 0 plus -8 is -8. Multiply. 1/2 times -8 is -4. And add it. 4 plus -4 is 0. So we found another one. Okay, we got another root. Now, it turns out to be the same root that we had before, but that's okay, because those can count as two roots. Even though they're the same number, they count twice. That's called multiplicity. Sometimes you can have a polynomial with the same root multiple times, and it counts as, when you're counting the roots, that is, it counts as another one. So x equals a half, those count as two roots, even though they're the same root. And sometimes you call that multiplicity. So if the root appears twice, we call that multiplicity 2. Okay, and sometimes you'll see it when people list the answers. You'll see it listed once, but there'll be a little notation at the end that says multiplicity 2. Okay, that means it appeared twice as one of the roots. If you had a root that appeared 3 times, you would call that multiplicity 3. You would say one of the roots is this with multiplicity 3. Okay, so it is possible to have the same root appear more than once, and that's called multiplicity. And that counts as separate roots when you're counting the number of roots, making sure that it matches up with the degree, even though it's the same value. Okay, so we would say that x equals a half with a multiplicity of 2 is one of the roots. Okay, so now at this point, we should be down to a quadratic. Remember, our strategy was we had to find 2 roots to reduce it down to a quadratic. Since we started with x to the 4th as our degree of our polynomial, we need to find 2 roots to reduce it down to x squared, quadratic. And then at that point, we can dispense with the trial and error, and we can go straight to the solution. So at this point, we should be ready to solve it directly. Okay, so if we look at our remainder, our quotient polynomial, negative 8 is a constant. Negative 16 would be x, and positive 16 would be x squared. Okay, so essentially I have the polynomial 16x squared minus 16x plus 8. And I want to find the roots of that polynomial, so I just set it equal to 0 and solve it. Okay, so it's at a quadratic, so we know we're going to be able to do it no matter what. We might be able to factor it. If not, we can always use a quadratic formula. So no matter what, we're going to be able to solve this. Now, what I might want to do is I notice that 16, 16, and 8, those coefficients, those are all, there's a common factor of 8. So to make things a little bit nicer for myself, what I might do is just factor out that 8 as a common factor. And so when you're solving that 8, since it doesn't have any x's, variables attached to it, doesn't affect the solution. So for the purposes of solving, we can essentially ignore the 8. We can just look at the remainder polynomial, 2x squared minus 2x plus 1. Okay, so we got to solve that guy. Now, I mentioned before, I kind of like factoring, but you're going to find in this case, if you tried to do it, you wouldn't be able to factor it. It's not factorable. So you can't find combinations of integer coefficients that will allow you to factor this. Okay, but that's okay because we always do have the quadratic formula at our disposal. So barring factoring, you always have the quadratic, negative b plus or minus the square root of b squared minus 4ac all over 2a. So you can have that guy as your last resort. Okay, so if I solve that with the quadratic formula, QF quadratic formula, what I get is that my solutions are 1 plus or minus the square root of 3 all over 2. Okay, so quadratic formula gives us those two. Now it's 2 because it's plus or minus. So in the quadratic formula, you know you have the negative b plus or minus the square root part, and that actually represents 2 roots. One is the plus, so one root is 1 plus square root of 3 all over 2, and the other is 1 minus square root of 3 all over 2. Okay, so this actually represents 2 roots. Okay, so if we make a count, do we have our 4 roots? Since we had a degree 4 polynomial, we should have 4 roots. Well, yes, we do. We have 1/2 and 1/2. Those count as 2 roots, even though they're the same value. Say they're multiplicity 2. And then we have 1 plus root 3 over 2, 1 minus root 3 over 2. Okay, so we're done. So what are our roots of our polynomial? What are the x-intercepts? Okay, well, let me write it as a set. Some people kind of write it as a set. So we have 1/2. 1/2, you can list it twice if you want, or you could just say 1/2 with a multiplicity 2. Then I have 1 plus root 3 over 2 and 1 minus root 3 over 2. Okay, so these are the set of our solutions, our x-intercepts for that polynomial. Okay, and again, sometimes what people will do is instead of listing 1/2 twice, they'll say 1/2 with a multiplicity 2. Okay, so multiplicity means that it appeared twice. So if I say multiplicity 3, if I say that a root had multiplicity 3, that means it appeared 3 times. Same root appeared 3 times. Okay, so those are our roots. Now, you could extend this process indefinitely. So if I gave you, as my original problem, if I gave you, say, like a 5th degree polynomial, all that would mean is that I'd have to find 3 roots via trial and error before I could solve it with a quadratic formula or factor. So it just means a longer process. So in theory, I could give you any polynomial at this point. So you should be able to handle, in theory, any polynomial. So if I gave you a 100th degree polynomial, okay, well, in theory, you should be able to do that. You just have to find 98 roots by trial and error from the rational root theorem before you could actually solve it with a quadratic formula. Not going to be a pretty problem, but still doable. Okay, so you got a lot of power. You learned a lot now. And that's the power of math, is once you know how to solve it for a fairly small problem, you can extend it, and same process, just on a bigger scale. So you just scale it up. Okay, so that's the rational root theorem. Okay, now, as you've discovered, sometimes this list of possible roots can be pretty intimidating, pretty daunting. Lots of stuff in this list. So you might be wondering, well, okay, is there a way that I can narrow things down so that I don't have to search through all of them? Well, the answer is sometimes there is. I mean, if you can use logical thinking, sometimes you can find some observations that may allow you to narrow the list down. Not always, though. Sometimes you just got to start. So for example, like if I had a polynomial where all the coefficients, say, were positive, if I had a polynomial with all positive coefficients, that would probably tell me I would need to start trying negative numbers from this list, because remember, eventually we got to get it down to where something cancels off something else. So you got to start to introduce some negatives in there. Okay, so if I had a polynomial with all positive coefficients, then it would probably make sense logically to start checking the negative numbers first. And in the same way, if I had a polynomial with all negative coefficients, then I would probably start to check all the positives first, because for the same reason, at some point, I've got to get stuff to cancel off and give me 0. Okay, so it's things like that that you can kind of sometimes take advantage of, but not always. So sometimes you just gotta bite the bullet, and you just gotta start trying it out. Okay, so these are kind of neat problems, kind of fun, but in some ways kind of tedious, because sometimes there could be a lot of trial and error. Okay, and now you see why in the beginning I mentioned that you're going to want to do this with synthetic division. I imagine in trying to do this trial and error process with long division. I mean, it's doable, but not very practical. Okay, so here we are. Here's the rational root theorem for finding the zeros, the roots, the x-intercepts of polynomials.